So welcome back to another video. So in this video I'll be showing an antenna design which is basically used for biomedical applications. So this is part 1 video. So I'm going to detect whether brain tumor is there or not. That's what the project I'm going to work on. So the first part of this video will leads about the design of microstrip antenna, and that especially work on UWB, that is from 3 gigahertz to 10 gigahertz frequency range. So what you see on the screen is basically the microstrip that I designed, and you can see that this is the front view of the microstrip antenna, and which is basically start with a basic rectangular kind of microstrip, and we have do some modifications like I have before that I will show you what are the dimensions of this particular antenna so that you can able to replicate it. So the total surface area of this antenna is, show you, it's the x-axis value, that is 31 cross 31 to 31, so it's around 62 millimeter. That's what the width of the antenna, and the length of the antenna is around 24 to 24, that is around 48 millimeter. So that's what 62 of width as well as 48 of length. That's what the dimension of the total surface area of this microstrip antenna. And in this project I have chosen the substrate material as FR4, flame retardant material, which having an epsilon value, permittivity value of 4.3, and the thickness of this particular substrate is around 1.6 mm. And coming back to the other two layers, one is your ground layer. So basically I created initially the full ground, and I have done the parametric sweep for the ground length, and the length what I given here is around 1/3 of the actual surface area of this microstrip antenna. So the length of antenna is kept similar to the normal substrate, that is 48 of length, and the thickness, the ground layer, which is basically the material is copper, and the thickness is around 0.035 that's what the copper layer thickness. And this ground length is actually I have taken, so it is around 18 length, sorry, the width of this particular microstrip is around 18 so which gives the maximum performance. So I have done the parametric sweep. So basically this is one method to achieve the bandwidth by reducing your ground length. So properly adjusting the ground length, you can able to get a wideband, or you can able to shift your resonant frequencies, or you can able to shift the return loss, the depth of your return loss as well. So that's what one kind of mechanism. So, and coming back to the top layer, that is your patch, which is again the same material like copper. Again the thickness is around 0.035 mm. So basically I design a square patch, which is here, you can see the highlighted. This is the square patch I initially designed, and after that I have attached the feed where the signal input is given to the microstrip. So that is a feed, and the feed I have calculated the width of the feed using the inbuilt calculator, which matches your 50 ohm impedance, and according to that only I have designed. And later I have created a circle cylinder which is having a radius, outer radius of, keeping the inner radius as 0 and the outer radius as 10, and I have cut the corner portion of this particular microstrip, and I have done this for both the bottom corners. So typically the shape will look like this. And finally I have done another one. This one I have done it using extrude option in CST. So if you wanted to know how to do this extrude option, how to know how to do this cutting, different kinds of cutting and all, you can post a comment in the description below, that I can create separate video for those tutorials. So here I used the extrude function, and I have created this rectangular kind of slots, and that's what the final design. And later on, once I completed this ground patch and this substrate design, the next part is to create the port. So you can see that the port is created over here, which matches 50 ohm impedance. So properly attaching a port is a significant thing. You need to avoid all the losses. So without by matching 50 ohm impedance, we will need to create the port. So that's what the design. Now we will discuss about the result part. So once we completed the design, we go for the simulation. So, and here you can see that in the simulation tab, the frequency range, that is the band of frequency that take one, is around 1 to 8 gigahertz frequency, which covers most part of your UWB. And once the result is completed, I mean the simulation is complete, we can see the S11, that is frequency versus reflection coefficient. So, and you can see that we have marked here, we will track for minus 10 dB in the y-axis, and if you draw a straight horizontal line across this graph, it will cut the graph in 2 points. So I have marked it as point 1 and point 2. So the point 1 I can mark it as the lower band frequency, so which is around 1.5 gigahertz, and the mark 2, again this minus 10 dB horizontal graph cut this graph over here, and that is around 6.5 gigahertz. So around 5 gigahertz bandwidth is achieved in this particular design, which we can say it as ultra wideband. And we have one resonation point. So the resonation point is, I'll put a marker. So the resonation point is around exactly 1.8 gigahertz. So that's what the lower band of UWB. So it start from 3.1, but since the application is brain tumor detection, so we need to get the resonation frequency in the lower band. So the reason behind this is that once we consider this this wideband frequencies, the lower band frequencies will be having the penetration, high penetration, and the upper band frequency will be having high resolution. So it depends upon applications. For example, if you are going to apply any image reconstruction algorithm, then definitely you need to focus on the higher band frequencies, which will be having high resolution capability. But if you are simply if you are going to analyze with respect to the S11, then definitely the kind of application you are using, then you need to get the response from the inner part of the tissues. So it need to penetrate, since if you go for any breast cancer or breast tumor detection, the breast is actually in the outside of the body, and there are very limited number of layers are there, example skin, fat and other tissues and all, and there is no bone involved in that. So the signal can easily penetrate through that. So in that kind of aspects, you can go to 2 gigahertz, 3 gigahertz or 4 gigahertz, depends on that. But if you are considering the brain tumor detection, definitely we have the skin and other thing, skull is there, then different layers are there, cerebrum, different things are there. So the tumor can be somewhere inside the brain. So in that aspect, the signal need to be penetrate through all the different layers. So that's why we are focusing on the lower band of this UWB. So this is the response, and the later part is that we will look into the VSWR kind of results. So here you can mention that the resonant frequency is around 1.8 gigahertz. So, and once we look into the VSWR, the same frequency, that is 1.8, that is your resonant frequency. So that's the same frequency range. You need to check the VSWR value, and theoretically the VSWR value is equal to 1, or it could be like less than or equal to 2. So it is satisfying 1.1. so the antenna is good antenna, the design is good, you can use it for this particular applications. And after that, once you complete the simulation, you can see that far field result is there. So in the far field, you need to simulate once again for the corresponding resonant frequency, because once you see the S11, that is your resonant reflection coefficient graph, you can able to identify at what frequency your antenna is resonated. Okay, so choose that frequency, your antenna resonation frequency, and for that particular frequency you need to calculate your far field, so that you can able to detect your E field radiation pattern, your H field radiation pattern, your directivity, your gain. All these parameters you can able to calculate for your resonant frequency. Okay, so here I can show you this. In the far field I have already calculated the far field AF is equal to 1.8, because 1.8 is my resonant frequency according to the design. So once you click on that, you have in the far field plot, you can see that we have an option 3D plot. So 3D plot will show you the three-dimensional radiation pattern, and here you have an option in the toolbar. You can switch between gain, directivity, all those stuff. So I initially selected it as directivity. So, and you can see that the directivity is around 2.5 dBi, and if you wanted to see the gain, so choose gain option over here. Gain is also in the range of 2.3, which is acceptable range, because gain should not go to negative. So here we are getting acceptable range, since the material is FR4, the maximum range is up to 4 or 5 dBi. So we are getting a minimal amount of gain and directivity, which is acceptable. And if you wanted to create a polar kind of chart for E field and H field, so you can able to generate E field radiation pattern and H field radiation pattern. So the option is like, here you have an option called phi cut angle. So if you put it as 0, that is E field radiation pattern, and if you given it as 90 degree, it will produce you H field radiation pattern. So depends upon that. By giving the value of phi, you can able to generate. So this is phi is equal to 90, which is basically your H field radiation pattern. So apart from this, you can able to generate current distribution graph, your efficiency of your antenna, and also you can able to plot. This is actually basically for F is equal to 1.8. you can see the directivity and gain. If you need to analyze a directivity and gain for a broadband, you can able to make a separate simulation for that. I will post one video for that. So this is all about the design part. So in the next video I'll show you how to create a head phantom and multiple layers of head phantom, and I will be radiating this this particular antenna against the head phantom, and we will see the response of this particular simulation. That will be in the next video. Stay tuned. Thank you.